Welcome back to our second panel, where we're going to be focusing not on the science quite as much as on the technology and on lunar resources. So we will have, again, Harrison SCHMITT will be speaking first, making some comments, then Jason CRUSAN from NASA headquarters, who's responsible for putting together a lot of these partnerships in the innovative technology area on advanced exploration systems. CHRISTIE IACOMINI, as head of advanced systems at Blue Origin, will speak about their plans for doing things with human beings, in particular, I believe, on the moon later. Yeah. And Angel ABBUD-MADRID from Colorado School of Mines, who's worked on topics on the resources on the moon. And finally, from industry, Dan Hendrickson, Vice President, Business Development at Astrobotic, who I'll also add was a student and now a graduate for several years back from the Space Policy Institute. And we're happy to have him here too. So with that, turn the mic over to Harrison, and good. Thank you. Good.
Well, some of you might wonder why I somehow or another became involved in the lunar resource side of things, besides sampling those resources. And it comes, I guess, all the way back to my father, who was an economic geologist in the southwestern United States, and actually around the world as well, who specialized in what are called non-ferrous metals. And I grew up as his field assistant, some would say his donkey, out in New Mexico. So I have had a long-standing interest in the economics of ore deposits. And believe me, the moon looks like it's a giant ore deposit. We just don't know whether or not it's a true reserve yet. We certainly know the resources are there. My first very specific involvement came as a result of being approached by Professor Gerald Kosinski of the Fusion Technology Institute at Wisconsin in 1986, I believe, at a conference, a nuclear power conference sponsored by Sandia Laboratories. I had given a keynote speech, which was just basically what it was like to go to the moon. And he came up to me and said, would you like to do some consulting with us on the resource base for helium-3? And I had to think for a minute back to Linus Pauling's freshman chemistry class and at Caltech, and helium-3, oh yes, of course. Helium-3, I knew nothing about helium-3 until I began to work with the Wisconsin group. The bottom line of it is that if it can be accessed, it represents an ideal fuel for nuclear fusion. If we had it on Earth, I'm sure our fusion power program and plants would already be operating using it. Helium-3 fused with itself does not produce any neutrons, and neutrons are the bad actors. That's what creates the nuclear waste. The tokamak system with deuterium-tritium is a giant neutron producer. It's about 5 times even the neutron production of a fission reactor. So you end up with a tremendous amount of waste, and unlike fission reactor waste, it can't be reprocessed. We ought to be reprocessing fission waste. Just a private little problem I have with President Carter about stopping that program. But nevertheless, helium-3 fusion is an ideal fusion process. It has some physics issues relative to other systems, but it has been demonstrated for a long time. Matter of fact, the first person to propose an inertial electrostatic confinement device was Farnsworth, the inventor of radar, as I recall. And at any rate, the physics is understood. The Wisconsin group has demonstrated helium-3 fusion as well as helium-3 deuterium fusion in small IEC devices. There has been significant technological project in other areas, some of it commercial, or at least with a commercial view of a process called P-boron 11. That's where you fuse boron isotope, boron 11 isotope with protons. But that technology is compatible with helium-3 fusion as well. The concentration of helium-3 on the moon, at least in the Apollo 11 large soil sample, we love to mention sample names, so 100084 is really talk about gifts that keep on giving. That's one, and it's all the result of Neil Armstrong. Can I tell you a story? Neil and I were talking about this one day, and he said, well, you know, the reason that I collected that sample was that I had put all the other samples I collected. He spent about 20 minutes actually sampling various rocks on the surface of the moon, and people didn't know where he was at the time doing this, good old Neil, and he put him in the rock box, the supposed vacuum sealed rock box, and he looked at it. He told me he was looking at it and said it looked awfully empty, so he just filled it up with 100084. And so we have a delightfully big sample from the Tranquility Base area of the moon. And when that is analyzed, finally back on Earth, after being split many times, sampled, split many times, everything, and we finally found that there was about 10 parts per billion helium-3 in the samples that were actually analyzed. Well, in my book, Return to the Moon, which deals with these issues, I did a bit of a economic geologist analysis of this other samples, and there are some impact breccias, what we used to call instant rock, formed by impacts in the same soil that contain about twice as much helium-3 and other solar wind volatiles than what's in the sample. So I believe we can say there's about 20 parts per billion helium-3. There's about twice as the quantity of solar wind volatiles in the lunar regolith as what has been measured in the laboratory because of these what I will call agitation losses. A great part of the solar wind volatiles are very loosely held. And in fact, Dave Carrier, a good friend of some of ours, has done some work in the geotechnical area, soil mechanics and the like, and was able to demonstrate that a significant amount of hydrogen is released when you agitate the actual lunar soils. So 20 parts per billion, what does that mean? If you could recover that, if that was a recoverable grade of the material of the helium-3 in the moon, then if you mined an area and processed an area of about 2 square kilometers, you could produce about 100 kilograms of helium-3. 100 kilograms would supply a power plant on Earth at a reasonable efficiency, large enough to supply the city of Dallas for a year. That's the amount of energy that is contained in this material. Very high energy content. Now the question is it economic? And that depends, number one, on whether you can demonstrate to the satisfaction of investors that you can build a power plant, actually build a power plant and produce electrical power through helium-3 fusion. It may be helium-3 or helium-3 deuterium. Helium-3 deuterium, I should mention, produces a few low-energy neutrons, but the waste that's produced in your reactor after a plant lifetime, is equivalent to hospital waste. It's not something that is very difficult to deal with. But the first thing that would have to be done, of course, is to demonstrate power plant scale fusion power is indeed feasible. And then the economics rests on whether you can actually produce the helium-3 on the moon, return it to Earth at a cost that's competitive with existing power systems. The primary existing power systems that one would have to compete with are coal and and natural gas. And both of those right now, natural gas has been fluctuating, as has coal, but it's still at about a $2.50 per million BTU price, as I used in my book for a model that I wrote 12 years ago. And as long as your costs will fit within that framework of competing with those, then you can look at it as having a competitive possibility as a terrestrial power system. Now, if investors decided to get into this, they would immediately probably put everybody else out of business in terms of lunar resources, because you produce tremendous amounts of hydrogen, about a third of which would come off as water when you're processing this. You produce a tremendous amount of oxygen, as if you break down that water. You produce nitrogen, solar wind carbon, and from which you can make methane. A number of things happen all of a sudden. You have this, in fact, one of your biggest operational problems is to figure out what do you do with all the byproducts that have been paid for by helium-3 fusion. So that's sort of my take on the long term of lunar resources, is that you have tremendous resource base on the moon. You don't have to just depend on the poles and water that might be available at the poles at 40 degrees Kelvin, which is an operational problem we haven't really dealt with very much, if at all. But still, in the long term, the moon can be a tremendous resource, not only for energy on Earth, but also for space-related consumables that we need in terms to go to Mars. Now, one final point, helium-3 fusion it looks like it's quite feasible for use here on Earth, but it is particularly of interest to interplanetary rocket propulsion. It works extremely well in a vacuum, and it is something to seriously consider if you want to decrease the amount of time getting to Mars, is to have helium-3 fusion rockets. My other colleague, John Santarius at Wisconsin, has done a great deal of work on this, and it looks like, again, if you develop the technology base for helium-3 fusion, you will have an interplanetary rocket technology that can solve some of the problems, not all, of cutting that time going to Mars down maybe by 2/3, hopefully, in order to reduce the radiation issue as well. Thank you very much.
I'm going to give you guys a little bit of an overview of activities at NASA in recent history, and then also a little bit of an update on where some of our activities are going as well, related to ISRU. So for more than a year, NASA's been studying kind of an orbital outpost concept, the Deep Space Gateway concept that we had. And now what we've seen is the transition from concept studies to actually policy implementation, which is a really exciting time that Robert talked about this morning. And now the role of the moon in expanding human presence into the solar system is really key for our activities that we want to do. But like many of our activities, NASA doesn't do this alone. In order to do a sustainable crew presence in deep space, it requires the best of NASA, our international partners, our academics, and our commercial industry actually all working together. Also, over the past decade, we've recognized a growing and emerging new players in the space industry, spaceflight industry, and designing an architecture around an architecture for human spaceflight and sustainable human spaceflight that recognizes that fact, and the fact that that will continue to change over time is critical. So the Lunar Orbital Platform, or Gateway, is the key first element that we're putting in place. It has a couple key attributes. It's not a space station. It is an outpost. It allows us to conduct missions to the surface of the moon, enable the critical infrastructure that we need for communications and transportation to and from the vicinity of the moon. It is an orbital platform to conduct science activities, as the previous panel talked about in much better ways than I could. And more importantly, it's the first kind of staging point for our entry into enabling humans into the solar system that we have. It's not by coincidence or accident the Gateway kind of architecture is a little bit flexible and resilient to policy changes. It's also resilient to industrial changes that occur over time. We've put a lot of concerted effort into interoperability standards for both us and our international partners, and the kind of emerging commercial space sector that's coming along. And we kind of see this public-private partnership model continuing to evolve NASA kind of started this effort, and we continue to see it evolve over periods of time. And in order for us to be able to leverage the dynamic changes that we see in the commercial sector, continuing to have the critical partnerships with our international partners, and then actually all the great research that's coming out of universities and university students as well, which I'll talk about a little bit. One of the key pieces about this architecture is, for the first time, human spaceflight kind of has a hub and spoke kind of architecture. You could actually read into this for the very first time. We have a refueling-based architecture for human spaceflight and a reusable basis for human spaceflight. The gateway in and of itself and our departure out to missions like Mars are all counting on the fact that we will do refueling in deep space. So this is opening the door to in-situ resource utilization and the capture of those resources once all the innovation in the world actually figures out how to do those things. It's particularly important, as we know, the gear ratios that we see from harvesting propellants in space to enable some of those opening frontiers or the reduction of mass that we need to launch. Recently, we're trying to expand our investments or the kind of funds that we catalyzed the industry and academia with. We just released in December an in-situ resource utilization, BAA, under our Next Step umbrella, which is kind of our engagement platform that we have for cost sharing of corporate resource contributions and such. So we've done this in habitation, we've done it in small satellites, we've done it for even our power propulsion element was a study effort under that as well. And now in-situ resource utilization. I'll tell you, the largest response we've ever received in any one of our calls that we've ever done to date. Over 50-some proposals we have, so thank you for the challenge of going through all that. It's a very robust response. We're looking at everything from focus areas of development of components and subcomponents to process, from atmospheric and regolith-based approaches that we want. We want to validate the technologies that we need to actually do the extraction techniques that are critical for this. Trade studies as well for critical architecture gaps. So how can we have a more ISRU-centric architecture, or how can we adapt and continue to adapt our architecture for that? So we're in the middle of those proposal reviews, selections that are in August, and this will be kind of a very first large cadre of awards that we'll do in this area to kind of really jumpstart the ISRU research that's been going on. In addition to that, quietly over the past, or not so quietly, given some of the panel members, we've been working on developing lander capabilities. We had an initiative called Lunar Catalyst. We're still in the middle of that. We're in year 4 of 5 years of effort at this point. In order to energize and enable the U.S. commercial sector, and it is a focus on U.S. commercial sector, after being able to create the commercial capabilities to land on the moon. Many of those commercial sector companies have international relations, though, and that's encouraged, and we continue to see that kind of evolve. And you saw from David earlier on his panel about Europe's involvement on expanding their domestic sector as well. This is an encouraging aspect, all the way to the point that we've now seen enough growth in this area that we now envision NASA, we are going out to buy commercial landed services for the very first time. That's a huge accomplishment by the agency and also by the industry that's actually going to provide those types of services that we have. In addition to that, we're actually looking at now scaling up to human class landers. So in addition to that, we have in the budget proposal, we have efforts to go after doing human class landers with a demonstration in 2022 and 2024 of at least 500 kilogram plus payload capacity there. We have an RFI that we're engaging industry, academia, and everybody else to get your inputs on how should NASA engage industry. What are the partnership strategies? What are the intellectual property concerns? What kind of cost sharing could be realized or not realized? Are our schedules realistic? People ask us, when should we or when can we land? I turn that back around to them saying, yes, when can we land? That's one of the inputs we want from the industrial base of where we're at and how we can get there. This is helping inform our U.S. side, and you heard from James and others about our European partners and international partners have their Heracles efforts. So we want to get our own house in order, per se, on the U.S. side so that we can fully engage our international partners to even increase the acceleration of activities that we have. On the university engagement piece, there's a whole set of strategic knowledge gaps that we have out there that help guide our investments. We continue to use those to guide our influence into the science mission directorate process for selection of missions and instruments and measurements that need to be done. But in addition to that, we have a couple specific initiatives that we've ran over the past now 8 years. our office has ran the CubeSat launch initiative. So for 8 years, we've been providing launch services to small satellites, primarily in the US, but even working with some of our international partners as well. That has, I would argue, given us the budding opportunity for deep space CubeSats, and now we're launching the first of those on our Exploration Mission 1 with a whole cadre of 13 of them going into deep space. But we couldn't have done that without the growth of the industrial base and the academic base, which actually, in a strange way, academia actually drove the growth of the industrial base for CubeSats. It was invented in the academic base, and it actually drove, and many companies now have spun out of academia into actually supplying and supporting that marketplace, which is just astounding to see. On the architecture side, we've been running a series of challenges under a heading called RASCALS, Revolutionary Aerospace Systems Concept Academic Linkages, which is, we like fancy acronyms sometimes at NASA, but it's called RASCALS. It basically looks at fundamental different architectures for human spaceflight, robotic systems. There's a whole challenge kind of aspect to it, where we select a number of teams, and this is actually in partnership with our National Institute of Aerospace colleagues, and they help us run that competition every year. This year's focus is on a lot of the architecture of Gateway and other activities that we've had. So we appreciate the 12 to 16 teams that kind of participate from around the country in those every single year. Another area is, in order to get through some of our hard technical challenges, we need a diversity of ideas and inputs. And I'm a big fan of open innovation. We have a whole series of activities under our NASA tournament lab where we put challenges out to the public in software and everything else. But we have a concerted effort under an initiative called XHAB. And XHAB is looking at very specific technical challenges. And we have engaged through Space Grant to put out those technical challenges. And we asked academic teams from across the country to not only solve the challenge, but how would they actually design curriculum around that, and a kind of a senior design class study that's with it. And with that, we provide a small amount of grant funding to actually help that. It gives the students a relative useful technical problem to work on that we actually want the answers for, and which is, so we were using those, so please don't screw them up, because they are very valuable inputs for us. And then at the same time, the innovation that the students bring to these challenges is just astounding. The new measurement, either measurement techniques or technology choices we get. I'll highlight one, even just, we had a school of design, Pratt School of Design in Brooklyn, go after habitat layouts. They're a design school. They're not an aerospace school. And they brought a whole different look at human factors to what we do. Amazingly different ideas than we would ever have gotten out of our NASA colleagues, no offense, on human factor design and such. And they showcased that up at the Intrepid Museum as well for the public, and it's been a great engagement that they do. We have been continuing to advance our in-situ resource utilization concepts and ideas and emission ideas that we have as well. There's the great Catalyst imagery that you'll see some great comments from my other panel colleagues as well, and the CubeSats initiative. I ran the original competition that enabled NanoRacks to be one of our key partners on the space station, and I negotiated the SpaceX agreement for that. I'll tell you, we never envisioned deploying CubeSats off the ISS as one of those things in that agreement. I can't remember the last number that Jeff has deployed, but it's over 200 and some missions off the International Space Station. So keeping aperture open to ideas, I'm a big fan of it. At NASA, I'm not here to judge ideas. I'm here to help enable an ecosystem and infrastructure for ideas to flourish, and more experiments that are out there. These are some of the great imagery from some of the student teams of RASCALS and XHAB, and you see everything from basically microgravity research in the large pools at the University of Maryland there to next generation kind of Mars simulated environments for growing plants on other surfaces. So lots of great ideas from the student teams, and just want to keep on encouraging that as well. So they're great. Thank you.
I'd like to thank the University Space Research Association for holding this timely discussion and inviting Blue Origin to participate. It's a really exciting time. I'm from Blue Origin, and at Blue Origin, we have a vision of millions of people living and working in space. That's been our vision since day one. Everything we do is in pursuit of that vision. To accomplish this requires transportation services and development of infrastructure, a lot of it. We've talked about this earlier today. We'll need systems to get logistics from Earth's surface into LEO and on to the destinations around the solar system that we want to explore. As we lean forward to develop this infrastructure, Blue Origin looks to the moon. We will need early prospecting, in-situ resource utilization, consumable storage for those products that we generate. We'll need power systems, communications, additive manufacturing, and someday habitats. It's a lot. We can't do it all, and it's going to take all of us to get it done, including commercial partnerships with NASA. Timely, so like I said, timely discussion. Just last year at Blue Origin, we started development of a lunar lander called Blue Moon. We're in a unique position, I think, to leverage many technologies and capabilities in its development, one of those being New Shepard. Our New Shepard vehicle is the first demonstrated reusable vertical takeoff, vertical landing rocket enabled with deep engine throttling capability. New Shepard now provides an environment to develop new technologies required for a return to the moon. A suborbital system with 100-kilometer apogee, New Shepard provides about 3 minutes of milli-G accelerations, an ambient flight environment for high-altitude atmospheric physics, technology development, and technology demonstration. Research has already been performed on New Shepard. In fact, some of it has been part of NASA's Flight Opportunities Program. And it's been done with multiple universities and multiple commercial companies. In fact, I have a good example, speaking of anecdotes. We just had an experiment on New Shepard performed by Professor Joshua Caldwell of the University of Central Florida. He had an experiment looking at how space dust combines to make planets or even the rings around planets. And there's extensibility of this to how we might interact with the lunar regolith. So it's kind of cool. I think there's a YouTube video of it. Anyway, back to our vision of millions of people living and working in space. New Shepard is obviously just a step, an important step. But the next major step is New Glenn. New Glenn is part of the heavy lifting infrastructure that will enable routine and low-cost access to space. And this routine and low-cost access isn't just to get us to the moon. That's what's going to be required to stay at the moon. New Glenn is our orbital launch vehicle in development to deliver people and payloads to LEO, GEO, and beyond, including the moon. Part of this infrastructure also includes New Glenn's manufacturing complex. And recently, it was open for occupancy, so we're making great progress. And our orbital launch site, Cape Canaveral Launch Complex 36. Key features of New Glenn include a powerful LOX methane, 550,000-pound thrust engine, the BE-4, a reusable first stage, which obviously lowers your launch costs, a fairing diameter of 7 meters, which reduces technical challenges and costs incurred by having to deal with complex packaging of payloads, and a delivery capable of 45 metric tons to LEO and 13 metric tons to GTO. Blue Origin's New Glenn heavy lift, large volume capacity enables us to take another step towards our vision, building the infrastructure required to return to the moon. That step begins with Blue Moon. Any future human lunar infrastructure will require the capability to land large masses on the surface. We've been hearing about the types of systems we'll need. Cutting-edge science rovers, resource prospecting, in-situ resource utilization, logistics support, and habitats. As we said, those are all going to be required. Blue Moon provides such a lunar transportation service with a medium to large payload delivery capability. Blue Moon is targeting a delivery of up to 10,000 pounds of useful payload. That's not including Blue Moon itself. That's not including the descent propellant. That's almost 5 metric tons of useful payload. Somebody in the office put it in perspective for me and said, that's like trying to land 5 Mars Curiosity rovers all at once. So, huge capability. Blue Moon could be launched on New Glenn. It could also be launched on NASA's own Heavy Lift Space Launch System rocket, the SLS. As I've been talking about, we're leveraging proven capabilities developed by Blue Origin on our new Shepherd system, BE3, BE4. This includes expertise in technology in vertical takeoff and vertical landing, in-house tank development and tooling, additive manufacturing, of course, liquid propulsion. We have a lot of in-house test facilities that we leverage. All this investment and proven capability reduces development time and risk. As part of a public-private partnership with NASA, we are willing to invest further. Blue Origin is privileged to benefit through NASA's announcement of collaborative opportunity, otherwise known as ACO. Specifically, we've been partnering with NASA Johnson Space Center and NASA Marshall Space Flight Center to exchange technical expertise in maturing liquid oxygen and liquid methane lander propulsion technologies that can enable new missions such as Blue Moon. It's been a great experience. We started this at the beginning of the year. It's not only just for us to speak with NASA, but also for the NASA centers to speak to each other. It's been a great conduit all around. We really appreciate NASA's creativity in providing that kind of opportunity to give us access to technology experts at the centers. As Blue Moon is on path for Blue Origin, it fits very well as a public-private partnership with NASA to participate in NASA's lunar exploration campaign, which includes the Mid to Large Commercial Lander Initiative. We, of course, encourage Congress to pass this budget and look forward to working with NASA's Human Exploration Operations Mission Directorate and Science Mission Directorate. And as I said, we are willing to invest alongside with NASA to make this a reality. We're reaching out to payload customers. Our first mission is easily sized to start lunar prospecting, including delivery of a rover such as NASA's Resource Prospector. We have a lot of work to do. We can't do it alone. We look forward to working with NASA to enable the return to the moon, and this time to stay.
This panel is about enabling exploration by technology and space resources. What is not explicit on this title is that lunar resources not only will enable future exploration, but they will also enable the new space economy. And this is an exciting time, just as Jason alluded to, and also Clive Neal in the previous panel. And this is important because you can already start seeing how government and private industry are going to have a very important role of making this happen. Now, what am I referring to this when I talk about both exploration and economy? It's important to note that when we start talking resources, lunar, Martian, or terrestrial, one has to know that a resource has value only by its utilization. If not, that's just an element of interest. And three important things are very key in order to utilize resources, and they go together all the time. You have to know your resources, where you're going. You have to know develop the technology to recover it, and as important as these two is to have a customer. These three things have to play together if we are to be serious about utilizing resources. So let's start focusing on the moon. Let's try to see what are some of the possible resources there. And as I go through this, feel free to pick the ones that you may feel is the most valuable. Again, always focusing on how to enable exploration and space commerce. From science, we have learned in the last 60 years that important elements on the moon include 45% of that is oxygen. It's tied to the rocks. 21% is silicon. The sun has been bombarding the moon for billions of years, and in that process, putting particles in the lunar regolith, such as hydrogen, nitrogen, carbon, helium, even a special isotope of helium, helium-3, that Dr. Schmidt alluded to. We also have plenty of metals, iron, magnesium, titanium, nickel, even gold in parts per thousands on the lunar poles. Rare earth, which are so valuable for the renewable industry here on Earth. And as a result of several missions, has been found that the probability of having water on the lunar poles. When we look at all of this, obviously all of them will be key in order to have resources for humans and for robots. But the key point here is in terms of what is more valuable, is this on the short term or in the long term? And which one of this one is more valuable for exploration and lunar commerce? And it turns out that out of all these elements, the most valuable in the short term is plain good old water. In water, you can start thinking, yeah, that's for drinking or growing plants or shielding you against cosmic rays, but not. No, what I'm referring to is on the short term, water is valuable because you can split it out into hydrogen and oxygen, the most energetic rocket propellant that we know. And why is that valuable on the moon? It's because we're talking on a body that is 1/6 the gravitational force of Earth. Think about this, for 60 years, every propellant, every human consumable, every little bolt and nut has been sent from Earth. And as we can already see, that's a very energy intensive. This is a very expensive way to launch things into space. So it's not a sustainable or an efficient way if we want to continue doing exploration. So what about if we could have that water on a place that it could lower the transportation costs and then enable operations? Not just on the moon. You can transport this propellant that is generated on the moon to places like low Earth orbit or to the Earth-Moon Lagrangian point. And that, in that way, really constructing an infrastructure in what's called cislunar space that will enable lowering transportation costs and then many other commercial activities. This is not a new idea. In fact, the very first study that was done on the prospects of using lunar ice was done by academics. And it was done at the Colorado School of Mines, spearheaded by Michael Duke, which was one of the early proponents of space resources, and I believe a colleague of Dr. SCHMITT in his Caltech years. And what this study found is that, indeed, if we can leverage from the water that is obtained on the moon, we can start lowering transportation costs significantly. Interesting enough, this idea came back 14 years later, not by academia, but by the private sector. One of the largest launch providers in the world, and that's United Launch Alliance, that conducted their own study and figured out that indeed, if one can refuel their upper stages in space, it will make business sense to them. And so they're in the process of developing their upper stage, the ACES upper stage, which can also be modified to land on the moon using a landing kit. And both of them use exclusively hydrogen and oxygen. No helium for pressurization, no hydrazine, exclusively hydrogen and oxygen. Why? Because that could probably at some point be obtained from space, and they will be ready for this. In a way that they can have a fully reusable high-thrust transportation system that can operate for many years without having to launch everything from Earth. Not only that, they came up with their own transportation system and trade routes, including low Earth orbit, the surface of the moon, LEO, and even included in some of their plans in the future to have a route going to asteroids where they can send their ACES to be refueled with water obtained from carbonaceous asteroids. That's a little bit more in the future. Again, I want to bring you back to the short term. And so what ULA did is that for the cislunar space, they came out even with a price point in order to see how they can beat their business case right now. And so what they did is look at the cost of sending propellant from Earth, which starts around $4,000 a kilogram. That's what they spend right now in order to do this. And that goes exponentially all the way up to 34,000 kilograms to put any payload on the surface of the moon. And they compare this to what it would cost if you do this from the moon. And they started by trying to beat their business case by starting at low Earth orbit with $1,000 less, $3,000 a kilogram, and then work backwards. Let's look at how much would it be to produce it on the moon, which is about $500 a kilogram, and then work backwards to see if they could meet their business case, and it closed. So that's extremely encouraging because ULA has become the very first customer, and that important three things that I mentioned at the beginning that can encourage the development of space resources. Now, the challenge was, can we find now a company or somebody that will make the business close from the supply side to provide the infrastructure on the moon to produce lunar propellant? And that actually was a study that has just been recently conducted in a combination of industry with academia. And it was done by the School of Mines, University of Central Florida, and United Launch Alliance that look at different ways in which we can extract the water and split it into hydrogen and oxygen, store it, and have it ready for a spacecraft to refuel. And so we considered a variety of ways. Typical terrestrial mining by using excavation, also drilling, in which you can have boreholes, sublimate the ice, take it to a plant, separate hydrogen and oxygen, and then cool it down, and then store it for a rocket. But it turns out that the best alternative we found was not one that we don't have here on Earth, because on Earth we don't typically go on mining for water. It's available everywhere. And that one is what we call a passive system, or thermal mining. And here's the infrastructure that you will need to do something like this. And what we did, we considered every aspect of this infrastructure and evaluated and made an economic analysis to see if the business case can close. So this is how this operation would look like. This is in one of the permanently shadowed craters on the north or the south pole. The power will come from sunlight that will be reflected from 3 different sets of 2 collectors on what's called the peaks of eternal light. And that power will be beamed for both powering the separation and the storage unit. By the way, it's really good to have 40-degree Kelvin, because then you can store your liquid hydrogen and oxygen without much energy. And some of that energy also will go through a transparent tarp, sublimate the ice. That ice will be cold trapped in a couple of 2 rovers that will actually go in and go to the separation plant. So with this, we remove as much as possible any moving parts and make it as free as possible to move around. And with this, we were able to develop, and we proved that we can develop and field a lunar mining operation and close the business case. In fact, we came below what the development cost was set by ULA. So what this tells you is that now you can have a customer, and you can at least have the idea that technology can be developed to extract lunar ice. And this will become even much more interesting when not just one company, but other companies like the ones we have here on the panel get into developing or using this propellant. And where not only NASA it's the participant, but when you have also the Europeans and the Japanese and the South Koreans and the Indians that have expressed interest on this field. Now we have the customer and we have the technology. What about that first thing that I mentioned, that we need to know if the resources are there? We need to characterize the reserves of ice if we want to then go ahead and do this. Well, that will be the next step. And that is a partnership that we are doing to conduct a workshop at the Space Resources Roundtable this June, in which we have School of Mines, also the League that Clive alluded to, and ULA, putting together what's called a lunar polar prospecting workshops, where government agencies, academia, and industry will get together to look exactly at how is it we can evaluate the ice reserves on the moon. Could it be done with CubeSats, with satellites, with softbots, or with rovers that we can go down and finally figure out the amount, the concentration, the distribution, exactly what we need to then start moving with technology in order to develop this. And hopefully from that we can get that information. What is important to know now is that if we have the capability of doing this, we will be able to develop an infrastructure on cislunar space that will lower the cost to get to the moon about 2x, and similarly to Mars, which is a significant reduction if we want to start really increasing exploration and commercial activities. Now, if you want to go to the rest of the solar system, then Mars will become the stepping stone to do that, but that's further down the road. But in the near term, what we can do right now with this push to return to the moon, or forward to the moon, as Carly said, the 2 key points that you have to take from this is that the cislunar economy will be the enabler for sustainable space development, and moreover, the moon and mining lunar ice propellant will be the first step to truly have resources enabling exploration and also the new space economy.
Good afternoon. Thanks very much to USRA and SPI for allowing us to speak here today. My name is Dan Hendrickson, and I'm from Astrobotic. We are a lunar logistics company based in Pittsburgh, Pennsylvania, and we were founded to primarily address this challenge that you see here on the screen. As I think everyone in this room is quite well aware, it's incredibly expensive to go to the moon, doing it the same way we've always done before, namely building spacecraft, taking those designs and then throwing them away after you achieve the mission, and basically reinventing the wheel every time you do it. We would like to radically alter how that's done by taking a product line approach and a shipping model approach to delivering uncrewed payloads to the moon. By taking the shipping model approach, we're able to lower the cost, we'll carry a variety of diverse payloads on a single mission, and we'll be able to offer a end-to-end service for all of our payload customers at 1.2 million per kilogram. We'll also be providing power, communications, and basically an end-to-end service that includes the spacecraft, the launch, and all the commodities required to carry out their mission. We do that with our Peregrine lunar lander, which you see here. Again, Peregrine is a product line approach. So again, we don't throw away the design after each mission. We want to reuse this design over and over again. It's very modular in nature, and it's designed to be a vehicle that can go to any latitude on the moon, could even go to the far side if it had a relay capability from orbit. And it's ultimately one lander for any mission profile. We emphasize high reliability and low complexity. We think this is incredibly important for our customers. They know that once you've successfully demonstrated this platform, it's important not to change it from mission to mission. And we work with a lot of proven providers and suppliers because, again, it's all about keeping that cost down. So this is a visualization of our product line philosophy. The core bus that you see here on the left is the main Peregrine lunar lander, which will fly on our mission 1. That first mission will be a key demonstration of service for all of our payload customers around the world. And then the configurations you see to the right are slight modifications that you can make outside of the core spacecraft bus to allow you to achieve any mission profile or any destination. So for example, by just adjusting and articulating the solar panel on the lander, you're able to go to different latitudes on the surface. By putting the payload decks in which the payloads are normally mated, if you move those out and place a large rover on the top of the lander, you're able to carry a significant single point mass like a large 300 kilogram rover to do things like prospecting or perhaps even extraction in the future. This is a look at our first mission configuration, again, focusing on demonstrating the service, demonstrating the core spacecraft bus. We'll be flying as a secondary on Atlas V. We're incredibly excited to be flying on Atlas V. It's the most reliable launch vehicle in the world. We'll be launching from American soil out of Cape Canaveral. We'll be carrying 35 kilos of non-NASA payload on board our mission. We've worked very hard to cultivate the payload market over the 10 years that we've been in business. Beyond that 35 kilos, we're also holding an allotment for NASA as well. As mentioned, we provide power and communications to all of our payloads. We have allotments per kilogram, just as the price is per kilogram as well. And I think it's important to note for the university audience that's here today, Mission 1 is especially well scaled for experiments, for investigations from the university community. Peregrine is very well designed to carry 1 to 10 kilo experiments and investigations, and that really allows for a wide range of types of payloads, say at 3U CubeSats, in lunar orbit, small rover deployments, resource instruments, seismometers, retroreflectors, all the kinds of payloads that universities would be well equipped to be able to build. As mentioned, Peregrine is a product line, and again, we don't change the core spacecraft bus from mission to mission. The first mission, again, will carry 35 kilos of non-NASA payload. The vehicle can get up to 265 kilos on future missions. And again, we only add an additional amount of fuel in the tanks that already exist and take a different trajectory, and that's what allows us to get to the higher payload capacity you see here. We're also going to be going to the moon early and often. Following the first mission, we're planning a flight about every year. So again, we're looking to have a steady, regular campaign, which again, I think is important for the research community because for the first time ever in a planetary environment, it'll be possible to follow up from previous investigations in a very short amount of time. We're very proud to say that we're leading the world in the payload sales market. We have 11 deals in place for our first mission, and I should note that all of these are paying customers that are on contract. We have 6 countries that are represented on this manifest that you see here. And one model that's perhaps particularly interesting for the community here today is the one that we have with the Mexican Space Agency. We're working with AEM. They used our definition information of our lander from our payload users guides, our interface definition document, to inform a request for proposals that they issued in country. The winner of that RFP actually is a Mexican university out of Mexico City that's now building the payload on behalf of AEM. So this is, I think, an interesting model for space agencies to consider going forward, and important for perhaps NASA in the future might be able to also utilize this, this method of working with universities and space science researchers. We're also proud to say that we're leading the world in the technical development of commercial lunar landers. We have 10 years of lander development work that we're leveraging for the build-out of Peregrine. We very much owe a huge sum of gratitude to NASA and AES and Jason CRUSAN's office for instituting Lunar Catalyst. This has been a fantastic program that's allowed NASA engineers to work directly on the development of our program, shoulder to shoulder with our teams. Although they're working with us shoulder to shoulder, we still own all the decisions, all the design, all the build out of the lander itself, but we gain that expertise and wisdom from the space agency, which is really fantastic and very helpful. I think this is a really shining example of public-private partnerships that NASA has. And lastly, I should note that we have 24 NASA contracts passed and ongoing up to this point, so we have a very strong track record of delivering for NASA and our customers. I'm proud to say that the Peregrine lander is at a PDR status. It's a true industry standard PDR. We have a partnership with Airbus out of Germany, in which they come and they actually judge our PDRs as an independent review team. So they don't know anything about our program until they come blind, at least the reviewers, until they're in the room and they hear about our program. And in fact, they signed off on our Peregrine lander and said it is in fact at a PDR level. So we're very proud to have that designation. Now we're progressing forward towards CDR for Peregrine. As mentioned, we're partnered with NASA and Airbus. We also have partnerships with DHL. So the world's largest logistics provider is a multi-million-dollar sponsor of our program. Incredibly exciting to have DHL on board. Just as they ship for folks around the world, we're going to ship to the moon. So they see a very strong thematic connection. And it's always exciting to have non-space actors join our community. And they clearly see that there's a future here. So it's exciting to see our economic sphere in a very real way is expanding out to the moon. And lastly, as mentioned, we're flying with ULA. We're very proud to be partnering with ULA. As the last presentation noted, they're very forward-thinking. And again, they have the world's most reliable launch vehicle in the Atlas V. And so very glad to be flying with them. And all of our customers are also very glad to be flying with Atlas V. So I just want to step back for just a moment and say, I think there's a really unique opportunity that we have right now with the deep space architecture that's being developed. It's very exciting to have Orion and SLS coming online to send crew and significant amounts of cargo to the cislunar environment. And then the Gateway being built and being a part of that, I think is a really great leverage point to also work with robotic landers like Peregrine. There's a whole variety of different types of activities that this specific architecture can take advantage of and leverage. And I think it's not trivial to note that this ecosystem is very real. It's very much in development. Of course, we're seeing great progress, great hardware being built on those 3 exploration architecture pieces. And then again, Peregrine on the commercial side is rising to meet those capabilities and work together in synergy. It's not, I think, an insignificant moment for us to recognize that we are truly on a forward path toward the moon, and here's the proof of that. So with that in mind, there's a couple of mission profiles that I think that the Gateway, working with SLS and Orion, and Peregrine can enable and allow us to finally address some long-held objectives that NASA and the space science and research communities out of universities have long been wanting to address. For instance, now it's possible to do telerobotics in cislunar space from the Gateway. You could have landers on the surface, robotic landers deploying rovers. You could eliminate the latency issues going from the Earth to the moon by utilizing Gateway to lander to rover. The Gateway itself can serve as a comm relay for landers that are on the surface at maybe some difficult places to operate, like say the far side or polar regions. It's possible to gather samples robotically, bring them back to Gateway, put them on Orion, send large caches of lunar samples all the way back to Earth. And then, as mentioned by a number of folks here, the interest in water ice and harvesting that is very strong. And this is, I think, a really smart progression that allows us to utilize Gateway to perhaps do the first tech demonstration of transfer of volatiles for potential utilization. So you could have, for example, Resource Prospector, as the mission that's been mentioned a few times here, could do initial prospecting at the surface, and then as a follow-on, using Gateway, you could actually do a tech demo related to the utilization of those volatiles, assuming that you've proven that there is ground truth at the surface and that they are in the amounts that can be utilized. So this is a pretty unique opportunity, I think, to leverage all of these architecture elements together in our forward path to the moon. And in this last slide, I might look like I've coordinated with Clive and Carly in saying the new moon is very real, but it is. This isn't a back to the moon. If you look at it through the lens of science exploration and commercial opportunity, there truly is a new moon that lies before us. Finally, we'll have the opportunity to do all of these long-standing objectives of prospecting resources, extracting resources, doing large cache sample returns in multiple locations to get that survey that the space science community and the geologists want to have. There's lunar caves. We didn't even know that except for a number of years ago. We made that discovery as a community that there's now a very well understood network of lunar caves in the form of lava tubes. We can send robotic landers to those caves, peer inside for the first time. There's magnetic anomalies that have some interesting implications for radiation protection of future astronauts. And then, of course, there's been longstanding geophysical questions about the moon and planetary science that are just waiting. They're only 200,000 miles away from us, and we can get there at 1.2 million per kilogram now, which is incredible. So again, I just want to emphasize that with all these architecture pieces that are coming online, with the commercial sector rising to meet those exploration systems, working in tandem together, this truly is a sustainable forward path to the moon. And we're incredibly excited at Astrobotic to support that and look forward to hopefully passing the FY19 budget, because I think it's an incredibly important step that NASA will be taking to send lots of these sort of robotic landers to the moon, not only to address some of these objectives, but also to pave the way for future astronauts, which is really the best way to do it. You start with precursors. Thank you very much.
Certainly, I think what we've heard from the science earlier this afternoon and the industry and technology in the last few minutes that, strikes me as we're building serious infrastructure that's going to get us there with the possibility of perhaps really using the resources and profits someday to companies. It's still in the future. We're still working there, regardless of the newspapers. It's not tomorrow, but it sounds like they're really significant steps, partnerships with the government, and that there are honest things to do up there, not just dreams at this point. And it's very impressive. Should we take a few questions before we end? Wow, we got a lot. Yeah.
I'm Daniel Savin from Columbia University. My question is to Dan Hendrickson. It has to do with the funding model that you envision for university resources using the platform. If we were to propose to NASA, they would provide funding and the flight vehicle. Are you folks going to be providing the funding for the university research to build these experiments?
Sure. So we very much want to enable university science, and we're very excited to do that at the 1.2 million per kilogram. But we do recognize that is still a tall order for the university community to pay for that directly. So we are kind of exploring a number of different models. Again, I think the AEM model is a very interesting pathfinder. That's an internationally focused one that doesn't necessarily answer how do American universities pay for their payload opportunities, but I'm hopeful that as the lunar exploration and discovery program gets underway at NASA, there could be an angle for a payload call in which they're able to then apply for funding to fly on commercial providers. I'd probably leave it to Jason to maybe speak to that a little bit more. I don't want to speak on top of that, but I think there are some models that are being thought about along those lines.
Yeah, so we absolutely are planning, and I'll speak for my science colleagues a little bit. There is plan both on the science side and on the technology and human spaceflight side to issue payload development calls. In fact, science has actually stepped out already on a few of those. And there'll be more to come. And it'll be much like the models that you have today, where we fund instrument development, capability development, measurement development type activities, and NASA then goes out and provides the launch service in a lot of cases as well. But there'll also be an opportunity, much like CubeSat world, where it's a fully funded effort, not just the instrument development, also the flight as well, and allow you guys to work with industry directly. So we see both models in the future for that. That's why, but that's also why we're kind of leaning forward on the NASA side. We will buy landed services. We don't have a bunch of instruments developed in-house, so we develop that with all the institutions we typically do, and we intend to use those landed services for those instruments. So it'll be, think about the same models we use today, but now that delivery to the moon is one of those capabilities.
This all sounds brilliant and well thought out, and I know these ideas like the space shuttles and ISS were good ideas, but they ballooned, the cost got really high rather quickly. have we learned from certain mistakes in the past? How are we better positioned to keep the focus on doing this within budget and actually something feasible and profitable in the long run?
Yeah, so I'll address it from the NASA side. So first off, for the small landed services, I'm not building them. I'm buying them. So and we're going to have a competitive environment that's out there with multiple industry players actually doing that. So very much so, we're going to use the competition factors to drive costs of the landing type capabilities down. Implementation of gateway. So implementation of the gateway, we are in the acquisition phase of buying the power propulsion element for the first step of the gateway. We will buy that as a fixed price thing at the end. The synopsis is out in the street. The draft BAA is actually going to be released very soon. And we're going to go buy that and rely on the industrial base that's out there to buy that in a competitive environment, to buy a power and propulsion element, the first element of the gateway. And I'll tell you, on our first study contracts, we awarded 5 different study contracts for a multitude of companies across the U.S. There is a competitive environment out there, and they are hungry. A lot of it stems from the geocommunication satellite industry and other industrial bases that exist in the country as well. Our logistics flights for Gateway will be competitively awarded logistics flights, much like we do cargo services to the ISS today as well. Habitation, that's a little bit different. We're not talking about a large habitat like the International Space Station, though. We're talking about something on the order of 100 cubic meters of volume versus something about 8 times the size of that with the International Space Station. So the habitat that we have and the human-tended aspect of it is significantly smaller in size and scope and complexity. And us and our international partners are absolutely in discussions on how to go implement the habitats for the habitation capabilities we want for the Gateway as well. So I think we have learned quite a bit, and this is with the leverage of public-private partnerships that we're using to do that, and the leverage of the industrial base that we have for the U.S. side, and the leverage of international partners, of us coming together to build the kind of things that there isn't huge and commercial use cases for out there yet at this point. But I think it's, if you look at the budget request for Gateway, it was $2.7 billion or so. That's a significant reduction in cost compared to previous systems that we've done.
All the way back.
Keith Count, SOH.com. For Jason, the other day, actually, I think it was yesterday, Bill Gerstenmaier said that y'all are going to do this Gateway thing with a flat budget, not adjusted for inflation. Now, the question before about NASA being able to stay within its means and just between Constellation and Station, NASA doesn't do big projects on the schedule on the budget. You talk a lot about international partners in the commercial sector, which to a lot of people sounds like a common sense, a global approach to doing this. Yet the White House has put a position out that says quite clearly, bluntly, it's an American first space policy. How do you jive an approach that clearly seeks to spread the control, shall we say, to a far vaster audience than has been the case before, with the White House that wants it to be America first, and they say it about 15 times in the document? Okay, I mean, you're the stuckee. How do you reconcile it?
So I'll address it very simply, and I mean, yes, we want to grow our economic base of space activities in the U.S. That's very, very clear. That's a very clear policy direction that Scott has left for, and he would be the best to answer that for. But part of leadership and actually growing our industrial base, you've seen now even companies on the panel here who are multinational companies. They work around the globe for those endeavors. So you see that aspect even occurring in the commercial sector. It's also key to be a leader. Kind of U.S. first and the U.S. leadership. If you're not working with others, you're just leading yourself. So I think leadership is another key aspect of that of the policy that we're pulling on. Significant chunks of the Gateway are domestic, as you see. We do have very conservative efforts of building commercial capabilities for lander activities as well. But we will not leave our partners. We will work with the partners as well for that as a global exploration strategy. So it is a balancing act, though, Keith, as you note. But part of that partnership strategy, both commercially and internationally, is how you get sustainability for exploration.
We'll take time for one more short question. Steve.
Try to make it short. Steve Brody from ISU. 20 years ago, I was a lunar prospector, program exec for NASA, and also seeded some of the early ISRU work at Martin Marietta and others. So it's great to see where we are today, finally. But I'd ask, ISRU at the time, again, this is 20 years ago, we saw as a potential game changer. There's some other things right now on the table, like adaptive manufacturing, 3D printing, and inflatable technologies, et cetera, that could be game changers. I guess mainly for you, Jason, but for anyone, do you see enough investment and or research either from the government or on its own being pulled by other industries in some of these potential game changers that could change the dynamic of how much pounds we have to deliver to the moon per se or any place?
And so the advanced manufacturing part, I leave some of my colleagues at the industry side, the amount of investment that the industry is placing in advanced manufacturing far exhausts anything we could ever contribute in that area. Our knowledge base of next generation habitation systems and such, we've learned immensely over what we did with Space Station 20 years ago when the development of those systems started. And we can absolutely go about new approaches to reduce mass, increase reliability. Reliability is a key of those systems. ISRU has been a lagging area, so there's a concerted effort of this time with ISRU trying to really engage some of the marketplace. People talked about the 3 pillars of success of that. So you do need to bring on the commercial involvement on that, or you won't have the customer base. NASA's not the customer for these things. We can't be the customer. We are a customer, but we can't carry that whole watershed of that. But I think a lot of the areas have significant investment going on. I don't know.
Yeah, I think that the times that you were referring to is when we had 20 people in a room talking about ISRU. This whole area has exploded. Not only NASA was deemed to be the only customer, now you have companies coming and really being serious about investing on future technology. You got not just companies, but countries now involved in this. So the panoramic view out there has been changed significantly in terms of the value that space resources can bring to space exploration. And companies have been, I mean, you don't have this 20 years ago. It was hard to find. It was just NASA, and that was it.
Well, thank you. I'd like to thank our panel. I'd also like to thank our 3 students, Anna Uyghur, Jay Alver, and Cody Neifert, who have been helpful out front and with the microphones. And now to invite Steve Ackerman, who's chair of the USRA Council of Institutions, to join us in the panel and close and invite you to the reception. Thanks, Henry.
First of all, thanks for all the panelists and all the speakers today for a very exciting and informative presentations. So let's give another round of applause for those. Also, I'd like to thank Henry and the Space Policy Institute for helping USRA organize this, and particularly Henry for moderating it and doing it so effectively. Also, thanks to the folks outside the closed doors, as well as all the technology folks who made this possible, and all the mics and all those people behind the scenes that actually make this type of activity very successful, and for you all for coming. And the best part of my job is to invite everybody to the USRA reception. It'll be right down the hall, so go up the steps and go down a little bit, and it's on your left-hand side, and that'll be a good opportunity to continue some of the discussions and the ideas that these panels brought forth. So thanks, and see you in like 2 minutes. So run there because there's great food.